Intuition and the concept of reduced sample space. Welcome, everyone. Today, we are going to explore a very intuitive but powerful concept in probability, the idea of a reduced sample space. To start, let's look back at what we've learned in basic probability. Usually, when we calculate the likelihood of an event, we look at the entire set of every possible outcome that could happen. We call this entire set the sample space, which we denote as capital S. However, life isn't always played out in a vacuum. In real-world scenarios, we often receive additional information or a hint before an outcome is finalized. Think about a game or a scientific experiment. As new data comes in, our perspective shifts. This new information tells us that certain outcomes are now officially impossible, while others are still very much on the table. Because some options have been ruled out, the universe of possible outcomes actually shrinks. This narrowing down of our possibilities is what we call the reduced sample space. Over the next few slides, we will look at the mathematical logic behind this and walk through a concrete example to see it in action. Understanding the concept. Now that we have the basic intuition that information can shrink our universe of possibilities, let's look closer at how this works mathematically. When we are told that a specific event, let's call it event F, has already occurred, we no longer need to consider the entire original sample space, which we call S since we know for a fact that F has happened. Any outcome outside of F is now impossible, so we can simply set them aside. Instead, event F becomes our new, smaller, and more focused sample space. It is our new world of possibilities. So, if we want to find the probability of another event, let's call it event E, occurring. Given that F has already happened, we don't look at the whole original set anymore. Instead, we only look at the outcomes that are common to both event E and event F. This is what we call the intersection of E and F. Written as E intersection F, we then take the number of these common outcomes and compare them against the total number of outcomes available in our new reduced sample space, which is F. In the next few slides, I will show you exactly how this works using a practical example with 3 coins. Illustrative example, tossing 3 fair coins. Now that we have established the theoretical idea of how a sample space can shrink, let us move from theory to practice. To truly grasp this intuition, we are going to walk through a step-by-step example together. Imagine a scenario where we toss 3 fair coins all at the same time. Our primary goal is to find the probability of a specific event, getting at least 2 tails. However, there is a twist. Before we even begin our calculation, we are provided with a piece of prior information, a hint, if you will. We are told that the first coin shows a tail. As we progress through the next few slides, we will see how this single piece of information fundamentally changes our calculation. Step 1. Define the original sample space, $. Now that we have our scenario in mind, tossing 3 fair coins, let's move to step 1, where we define our original sample space, which we denote as capital S to start. We need to list every single possible outcome that could occur. Since each individual coin has just 2 possibilities, either heads, which we'll call H, or tails, which we'll call T, we can systematically map them all out. By looking at all the combinations, we get the set S, which contains HHH, HHD, HTH, HTT, THH, THT, TTH, and finally, TTT. If we count these up, we find that the total number of outcomes in our sample space, written as N of S, is equal to 8. Keep this number 8 in mind, because as we move to the next slide, we'll see how our target event compares to this total. Step 2. Define the target event, $E. Now that we have listed our original sample space, let's define exactly what we are looking for. Let event E be the event where we get at least 2 tails. If we look through our list from the previous slide, we need to pick out every outcome that has 2 tails or even 3 tails. So, our event E consists of the outcomes: head, tail, 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 head, tail, 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 head, and finally, tail, tail, tail. If we count these up, the number of favorable outcomes, which we denote as N of E, is 4. Now, before we move on to the new information in the next slide, let's calculate the initial probability. Without any prior information or extra clues, the probability of event E is the number of favorable outcomes divided by the total number of outcomes in our original sample space. That is 4 divided by 8, which simplifies to 1/2. Keep this value in mind, because as we will see in a moment, this probability is about to change. Step 3. Introduce the given information, event F $. Now, let's introduce the turning point in our example. Up until this moment, we were looking at the entire universe of possibilities. But now, we are given a specific piece of prior information. We are told that the first coin shows a tail. Let's represent this new information as event F. To see what this looks like mathematically, let's list the outcomes that satisfy this condition. We look back at our original list from the previous slides and keep only those that start with a T. So, event F consists of the outcomes T, H, H, T, H, T, 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 H, and T, T, T. If we count these up, we can see that the number of outcomes in event F, which we write as n of f, is equal to 4. Notice how our focus is already starting to narrow down from the original 8 outcomes we had earlier. Step 4. The concept of the reduced sample space. Now, let's bring everything together to see the magic of the reduced sample space. Remember in the previous slide, we identified event F as the condition where the first coin shows a tail. Because we are now certain that this event has already occurred, we can immediately discard any outcomes from our original list that don't fit this description. For instance, any outcome starting with a head, such as head 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 or head head tail, is now impossible. This is the core of our lesson. Our universe of possibilities has effectively shrunk. We say that our sample space reduces from the original set S to our new, smaller set F. So, looking at our screen, you can see our new sample space is simply equal to F, which consists of the following 4 outcomes: tail head head, tail head tail, tail tail head, and tail tail tail. As we move to the next slide, we will use this specific, smaller set to calculate our updated probability. Step 5. Calculate the probability of E$ given F$. Now that we have established our new reduced sample space, let's perform the final calculation. We are no longer looking at the original 8 possibilities. Instead, we are only looking within our new, smaller universe, which is event F. Our goal is to find which of these specific outcomes also satisfy our original target condition, event E, which was getting at least 2 tails. To do this, we look for the intersection of these 2 events. In other words, we identify the outcomes that are common to both E and F looking at our lists. The outcomes that appear in both sets are T, H, T, 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 H, and T, T, T. If we count these up, we see that the number of favorable outcomes in this intersection is 3. Now, to find the conditional probability, which we write as the probability of E given F, we take this number of favorable outcomes, 3, and divide it by the total number of outcomes in our new, reduced sample space, which is 4. This gives us a final probability of 3/4. Take a moment to make a very important observation here. Notice how the probability has changed. When we knew nothing at all, the probability was 1/2. But after receiving the information that the first coin is a tail, the probability increased to 3/4. This shift is the perfect illustration of how new information reshapes our mathematical certainty. Key takeaways. First, it is crucial to remember that information changes probability. As we saw in our coin tossing example, when we were initially looking at the whole set of outcomes, our probability was 1/2. But the moment we received that extra piece of information, knowing the first coin was a tail, the probability shifted to 3/4. This shows that additional information about an experiment can either increase or decrease the likelihood of an event occurring. Second, we have the concept of the reduced sample space. This is the heart of what we've discussed. When we are told that an event, let's call it event F, has already occurred, we no longer need to look at our original large sample space, which we call S instead. The event F becomes our new, smaller universe. We essentially discard all the outcomes that are no longer possible and replace the original sample space, S, with the new space F. Finally, when you are calculating these probabilities, you must focus on the intersection. To find the probability of event E occurring, given that event F has happened, you shouldn't look at the entire original set. Instead, you only look for the outcomes that are common to both E and F. This is the intersection of E and F. You then compare the number of these common outcomes against the total number of outcomes available in our new reduced space, which is the number of outcomes in F. All right, let's wrap up what we've learned today by reviewing the key takeaways from this concept. Keep these 3 points in mind, because in our next slide, I'll show you some common pitfalls where students often trip up when applying these rules. Common mistakes. First, watch out for the temptation to use the original sample space. A very common mistake is to calculate your probability using the total number of outcomes in the original sample space, which we call N of S, in the denominator, even after you have been given specific prior information. I want you to remember this rule. The moment a condition is given to you, your universe has changed. Therefore, your denominator must be the number of outcomes, specifically within that new, restricted set. Second, be very careful not to confuse the probability of the intersection, written as P of E intersection F, with the conditional probability, written as P of E given F. These are two distinct concepts. The probability of E intersection F refers to the likelihood that both event E and event F occur simultaneously, calculated out of the entire original sample space. S, on the other hand, P of E given F is the probability that event E occurs, specifically under the condition that event F has already happened. To make this crystal clear, let's look back at our 3-coin toss example. If we were looking for the probability of both events happening out of the whole set, P of E intersection F, the answer would be 3/8. However, because we were given the information that the first coin is a tail, we use the reduced sample space, which gives us P of E given F, equal to 3/4. Now, as we wrap up this lesson, I want to highlight 2 common pitfalls that students often encounter when working with conditional probability. Please pay close attention to these, as they are the most frequent sources of error in exams. Always ask yourself, has my sample space shrunk? If the answer is yes, your denominator must reflect that change.